because it's elevated, so you have the columns, right? Okay, so the problem 11.3 is looking at this part, the wall and the slab. Okay, so when we talk about water, earth retaining, water retaining structure design, is we are more actually looking on this part here. Okay, because here this is the lateral load. This part here is the vertical load, which you have kind of learned how to design the beam and slab for the vertical load, right? Okay. And there's another view of the rectangular. Okay, so I think most. So there's another. The circular, I have also shown you the circular. So this is a pressed water tank, pressed metal water tank. This is another pressed metal water tank. Okay, so. This is a circular, okay? Circular. The circular one is more efficient, but difficult to construct. So I have actually explained that before, because your formwork has a certain curvature, and then your rebar has a certain curvature. Okay. So, all right. Let's go back to. So here we are example 11.3. Okay, they look at this. They not only look at the wall, but also they look at the slab itself. Okay, so the wall is the detail of the wall is actually given in example 11.1. 11.1. Okay. In the here, the moment here is 14.6. They calculated for you. 14.6 kilonewton meter. Okay? 14.6 kilonewton. Okay. How do we calculate the, let's say I have this wall here, right? This wall here, this slab here. Okay? So what we have is we have the water. Okay? We have the water. And then the water will exert horizontal load. Okay. In your RC1, basically you design for vertical load, right? Your slab, your beam, your column, okay, your footings, and so forth. Okay. This one is the lateral load. Okay. So the lateral load from the water. Okay. In our next topic, the earth retaining structure, we have the lateral load from the earth. Okay, and then in the shear wall we have a lateral load from the wind, okay, and also from the earthquake. All right. So this is the more or less the first time that we deal with the lateral. Okay, we deal with lateral. So this wall here basically is a cantilever structure. Is a cantilever structure, right? So let's say this is gamma water. Unit weight of water. What's the unit weight of water? Anyone?
9.81.
Huh?
9.81.
9.8 kilonewton per meter cube, right? Okay. Most of the time we take 10 kilonewton per meter cube. All right. Okay. So depends on how precise you want to be. I think in science or in physics, maybe you take 9.8 kilonewton per meter cube. In our engineering, I personally use 10 kilonewton per meter.
10 kilonewton per meter cube.
Okay, so water, I think, 10 kilonewton per meter cube. 10 kilonewton per meter cube. Okay, so water, I think, 10 kilonewton per meter cube. Okay, so water, I think, 10 kilonewton per meter cube. Okay, so water, I think, 10 kilonewton per meter cube. Okay, so water, it's good that you remember, right? But a lot of people do not remember. So normally my benchmark is, we start with concrete. Everyone know concrete is 24 or 25, right? Kilonewton per meter cube. The water is less heavy than the concrete, right? So water is 10, okay? And then the soil will be in between. Soil will be less dense than the concrete, but denser than the water. So soil depends on what kind of soil, right? If it is gravel, sandy soil, it will be less. If it is silty clay, more dense. So when we are talking about soil, we are talking about around 18 kilonewton per meter cube, which is less than the 24, but bigger than the 10. Understand? Yeah. So basically, these are the few materials that that we talk about. Okay. All right. Okay. So why do I say gamma water? That this is the water. So this is the maximum stress, right? The stress is starting from 0, linearly increased to gamma water times h, the height. Okay, times height. So this is h. Okay, and then you have the equivalent force, right? Equivalent force. Okay, how do you calculate the equivalent force? Huh? I'm sorry? Huh? How do you calculate? If I know my stress is 0 here, my maximum stress is gamma WH, right? How do I calculate the force? How do you calculate the force of a triangular stress distribution? Huh?
Using the area.
I'm sorry?
Using the area.
What area?
Using the area.
Okay, can you write that? Where's the force? Okay, that's correct. Oh, you are a little bit hesitant, right? So he is using the area. Area is what? This is a triangle area, right? Half base. What is this base? H, right? Height is gamma h. So here is 1/2 of gamma h squared. Alright? This is what you mean, right? This is what you mean, right? Okay. I look at it another way. Okay? How do I look at it? I look at it this is a linearly increasing stress, right? I look at the average stress. Okay? This will be the average stress. This will be the average stress, right? That means this one I go and fill this thing up, right? Okay? So what is this average stress? This average stress will be half of gamma h, right? This is gamma h. Average is in the middle, right? Will be, so this will be half of gamma h, average stress. Now, this average stress is a uniform stress, right? So, how do you find the force? Is the uniform stress multiplied by the area, or in this case, multiplied by the height, right? So, here is squared. That's why you have the 1/2 of gamma h squared. All right. Just now you try to calculate half gamma h and h, half base height, right? Okay. The way that I look at it is half gamma h is the average. Is the average stress. And average stress is uniform. right? And meter core multiplied by the length will give you the force. And this force is force. What's the units?
This one.
What's the units?
Kilonewton per meter.
What's the unit? This is the force, right? This is what I call, let's say this I call P, right? Okay. What's the force is P is equal to 1/2 of gamma h squared, right? So what's the units?
Kilonewton per meter.
Kilonewton
Kilonewton
per
meter.
meter. This is gamma is kilonewton per meter cube, right? Okay. This is meter. So the unit is kilonewton per meter. This per meter meaning what? Per meter width. Okay, it's per meter width. That means our wall we design based on per meter width. Okay, because the wall can be 20 meter. The width can be 20 meter, right? Very long, right? So we do per meter and then we repeat. Understand now? Okay? Yeah. Now, this is the average, this is the force, but this force is at the centroid of the triangular area, not in the middle. Okay? Alright. So the moment, so this force will cause this wall to rotate. Right? This is a cantilever wall. Right? Right? So the moment, so here you have an MS, service slope moment. Okay? And your service slope moment is equal to P times 1/3 of H. Right? This is your H, this is 1/3 of H. Alright? It's 1/3 of H. And your P is 1/2 of gamma H square H 1/3. So what you have is 1/6 of gamma H cubed. Okay? Alright? Just remember this. 1/6 of gamma H cubed. Alright? So, okay? So next time you just write the formula. Okay? No need to go through this. Okay? Just say it's 1/6 of gamma H cubed. And this unit here is kilonewton meter per meter. Okay? Okay. When you substitute, it actually comes out with kilonewton. Okay? Kilonewton. But the physical meaning is kilonewton per meter. That means per meter width, what is my moment? Okay? Okay. Right? Okay, so his M is equal to 14.6. Now, the way that the book calculate is a little bit different. Okay? He calculate as 1/2, 1/3, so 1/6. 1/6 of this 19.2 is gamma H. Okay? So 1/6 of gamma H cubed. Then he plus another term here. Okay? So the reason he plus another term is because in the British code, I think mainly in the British code, in other codes, for example in the US codes, we actually ignore this term. Okay? Because in the British code, they consider the effective width in a cantilever this is a cantilever beam, right? Okay. So cantilever beam has a clear span. is a clear span, right? Okay. So normally when we say that L is actually the clear span. In the British code, they do not look at the clear span, they look at the effective span. So the effective span, they consider a little bit inside, okay, which is half a B inside, half a B inside, okay. So that is why they add this term. This wall here is 200, right? So the D, when you minus the cover and the rebar, so it's roughly 150. So basically it extends 1.5 D inside. Okay, but and this is in the British code. British code says, you know, when you look at the cantilever, the effective span of the cantilever is this. Okay, but most of the people, I just basically I kind of just ignore it. I just take the clear span. Okay, I just take the clear span because mainly because I started my career in the US, so we all design based on the clear span. Nobody questions. And the other reason is because when this thing is going to fail, it's going to fail here, not fail inside. So we are looking at the moment here. Okay, so that's so anyhow, but when we respect the code of the British code, so that's why I point this out. But in my test, I mean, you can ignore this stuff. You just use that 1/6 of gamma H. Okay, this 19.2 is coming from gamma H. Okay, all right. Understand? Yeah. So this is gamma H already. Okay. So that's why you have gamma H, gamma H cubed, and 1/6. All right. Okay. So here 14.6. So now we go back to this is 13.3. So we go back to 13.1. Okay. So here remember this is 14.6 kilonewton meter. Okay. Okay, so here the wall section shown in figure 11.7, okay, this is 11.7, is subject to a moment of 14.6 kilonewton meter. Okay, this 14.6, that's where it comes from. Okay, but I mean the author didn't tell you that how this 14.6 come about. So it actually comes in the example 13.3. Okay, anyhow. Okay, can I wrap this up now? This portion? Yeah, all right. 14.6 kilonewton meter. Actually, kilonewton meter per meter. Okay, per meter width. Under working loads. This is working loads. Not factor yet. Okay, not factor yet. Which may be considered as purely hydrostatic. Hydrostatic, that means the water is in static mode. That means the water is not flowing. Okay, we have hydrostatic and hydrodynamic. Okay, hydrostatic, that means this water tank, the water, just static there. Okay, all right. Hydrodynamics is the force caused by the running water. Okay. Okay. The moment acts so that there is tension in the phase adjacent to the liquid. Okay. So the water tank is like this. This is the water. Okay. So you have two phases. Outer phase, right? Adjacent to the air, right? Inner phase, adjacent to the water, right? So adjacent, so you have, here it says that tension in the phase adjacent, because our moment is like this. So this is in tension, this is in compression. So the tension is adjacent to the water. Huh? So tension is in the face adjacent to the liquid. Yeah. A grade C35A concrete which mount steels are specified and appearance is not critical. Okay. Okay. Here they use a concrete grade C35A. That means C35A is kind of like equivalent to C40. Okay, C40. In terms of the cement content. Okay. That means it's higher grade. Water tank will require higher grade because you want durable concrete. Okay, because it is in contact with water. You don't want you want to be more resistant to water penetration. Okay. Here they use mount steel. Mount steel, that means mount steel mount steel, the yield strength is 250 MPa. Okay. So we have high tensile steel and mount steel. Okay. High tensile steel are the rebars that has the indentation. Mount steel is the round bars. Okay. Yeah. And appearance is not critical. When we say appearance not critical, that means you can have tight width of 0.2 millimeter. Okay. When it is critical, that means you control it to 0.1 millimeter. Okay. Yeah. When we say appearance not critical, that means we allow water stain mark, because when water seep through, it will leave some stain. Some stain, right? Okay, so then if you are not too particular about it, then you can control it to 0.2 millimeter. If you don't want to see the water stain, then you control it 0.2, which is more strict. So 18 millimeter plywood formwork is to be used. So the formwork is plywood, not steel form. Okay, normally our form is wood form or steel form, right? And this has implications when we come to design for the temperature and shrinkage factor. Yeah. Minimum cover 40 millimeter, okay, which is quite a lot, quite a fair bit. Normally slag is cover is 20 to 25 millimeter slag, right? So in this case we have 40 millimeter. Okay. First assume D is equal to 150. So the thickness is 200. This time I've shown the wall. Okay. The D is 150. Okay. Right. And I think this is a liquid sand. A liquid sand. So that means the moment is like this. This is the tension. Okay. Okay. For a wall, okay, for a wall here. Okay. Now, a wall, you have the height and you have the length, right? Way across. Basically, our reinforcement, we have both vertical reinforcement and horizontal reinforcement. Okay. You have this is the vertical reinforcement, and also we have the horizontal reinforcement. Yeah. So this is the vertical reinforcement because this is looking at the plan view. So this is the vertical reinforcement. This is the horizontal reinforcement. Okay. So we are going to look at the vertical reinforcement first because our moment is like this. So our part of our vertical reinforcement is to carry tension. Okay, carry tension. So in this case, this is carry tension. Okay, this is carry tension. Okay. Now, he looked at the ultimate limit state first. Okay. Now let me explain why they start their starting point is the ultimate limit state. Okay. The ultimate moment will be 14.6. This is surface slope moment, right? Multiplied by 1.4, not 1.6. Okay, that means they consider the water as not as a live load, as a dead load. Okay, as the dead load. So here with 14.6 multiplied 1.4 is 20.4 millimeter kilonewton per meter width. This is the ultimate moment. So from the ultimate moment, you run through M1 BD square F sub Cu, and you get the moment arm, and then you get your steel, okay, as 604 millimeter square per meter width. So this part, I will not go into detail. Most of you will know how to do it already, right? So based on the factored load moment, you have this reinforcement, 604 millimeter square divided per meter width. Okay. Now, look at this now. This could be provided by 12 millimeter bars at 150 millimeter center. Area is equal to 754 millimeter square per meter. This is 754. This is 604. This is considerably larger than this. Right? Right? This is, I think, you could be saying maybe around 25%. You use the 754 divided by 604. What's the value? What's the ratio? 1.25, right? So that you can clearly see that he over-provide. Now, normally when we design, we do over-provide. Sometimes we over-provide 5%, you know, but we never go to 25%. So the question why? Why does the author wants to over-provide 25%? Because he knows that he need to over-provide this. Because if you don't provide this, over-provide so much, the rebar stress will not pass the test. Okay? Alright? The rebar stress will not pass the test. So the next thing is you go and calculate the rebar stress. And you find that even you over provide 25%, the rebar stress is still more than the stress allowed. Okay? Alright. So now we come and do this MS, FS. So we already know what is MS, right? Which is 14.6. Yeah, 14.6. So AS is 754, right? 754. Okay. Then we do the D. D is 150, right? D is 150, right? So to do that, we need to do the end row, okay? And also we need to do the reinforcement ratio. So AS is 754, D is 150. What is this B? What's the B?
1.
Huh? Sorry? So okay, so yeah. Now we go and do the serviceability limit state. Serviceability limit state, let me see, is trying to calculate the rebar stress. So in order to calculate the rebar stress, we need the modular ratio, right? As well as the AS over BD. Okay? The modular ratio is ES divided by EC. Look at how he divided by 2. That means he is accounting for the creep effect. The creep effect tends to reduce the modulus of elasticity of the concrete. Okay? So in this case, 14.8. So in the test 2, I will give these values to you. Okay? So you don't have to worry about it. But you should understand why we divided by 2. Okay? Because the creep effect, the creep coefficient is roughly 2. So here he calculates the 14.8, which is alpha C. In the book, the N, they call it the alpha C. Okay? Alpha C. Then what is this one? This is N row. Okay, so they try to calculate end row. Row is AS 754, D is 150, B is 1 meter because we are doing it per meter width. We are doing it per meter width. Okay. So we get this value is 0.074. And from figure 429, the book give you a table, okay, to calculate the x. To calculate this x here is KD. Okay, so this is calculated using the graph in the book. Okay, 0.31 is the K. Okay, x is KD. So 0.31 is K. Okay, now let's use this one, this formula to calculate the K, see whether it matches 0.31. Okay, so our end row in this case, end row is equal to 0.074. Okay, all right, and so you just do end row square plus 2 end row, take the square root, and then minus end row. Okay, so what is end row square? Plus 2 end row. So what's this value? Can someone give me?
0.153.
Huh? Without the square root, right? 0.153.
153.
Huh? 0.153. Is that right? So square root give you what?
0.392.
0.296. 296. Huh? 292.
392.
0.392.
392.
0.392. Okay, so now 0.392 minus n row, 0.392 minus n row is minus 0.074. What's the value?
0.3.
This one here. Okay, all right. Huh? So why does he say approximate 0.31? Because his graph here, the graph is not fine enough, so you have to kind of interpret exactly where is that value. Okay, all right. Huh? So this is K, so multiplied by D is 46 millimeter, right? 46 millimeter. So KD is 46 millimeter, right? So this is D minus 1/3 of KD, right? This one is D minus 1/3 of KD, give you the moment arm, right? And then divided by the area, give you the rebar stress. So the rebar stress is 144 MPa. Okay, now 144 MPa. This is a mild steel. This mild steel is 250, right? So 144 basically more than half of it already. More than half of the U strength. Okay, more than half. But where do we find the allowable rebar stress? The book has the values for you, but basically it comes from the code, which is 8007. Okay? The allowable steel stress in direct or flexural tension for serviceability limit. Okay? Remember, this is serviceability limit, not factor load, service load. Direct or flexural tension Fractional tension is due to moment, okay? Due to moment, which you find that in the rectangular water tank. Direct tension, we will find the direct tension in the circular tank. Okay? So the allowable stress depends on whether you are controlling the crack rate to 0.1 or 0.2. Just now, the statics is not important, so you will look at 0.2. So 0.2, this is plain bars. Plain bars is the mild steel. Fy is equal to 250. Deformed steel, which are high tensile, Fy is equal to 460. Okay, and this 0.2 is 115. Okay, 115. And just now, what do we have? We have 144. The calculated stress is 144. That means clearly this is exceeded the allowable stress. Right. So now we know that the rebar stress, just now the author has over provided by 25% of what is required for the ultimate load, and still it does not meet the allowable stress criteria. It's still exceeded, even though he has over provided 25%. Right? So what do we do now? Huh? I'm sorry? We have to increase the rebar area to reduce the stress. Okay? Because now, that means this stress is too high. Right? This stress is too high. So to reduce this stress, we increase the AS. Correct? To reduce the value, we increase the denominator. Okay? Right? So we increase the AS. So basically, he tried to have a quick way of doing it is to he just trying to proportion. So we say just try to proportion it. Okay. The allowable is 115. He got 144. The 144 is based on 740, right? So we increase it to 944. Okay, increase to 944. So now he increased to 944, which may be provided as 12 millimeter bars at 110 meter center area 1029. So he further increased this. Okay. Now why does he further increase it? Because this is actually an approximate in the sense that is underestimated. Why underestimated? Because Fs is inversely proportional to AS, okay? Provided that this thing doesn't change, then you can do that, right? But this KD, the neutral axis, depends on angle. So when you change the rebar, you actually change the KD. If you change the KD, you actually change D minus 1/3 of KD. So in that sense, you cannot just do using the inverse proportion to do it. Okay? If you do it, but you have to, but he understands that by doing that, he underestimated. Okay? So that is why I mean, he is actually an experienced guy, right? So in order to make up for that deficiency, he provided 1028. Okay. Right. And exceeds the alternate limit state support. So this one. So now to recap this, the starting point is to calculate the service load moment, and then he used the ultimate load moment to come up with the first estimate of the rebar area. Because to do the service slope analysis, to do this analysis, you need to know what is AS. If you don't know the AS, you cannot calculate the neutral axis. Okay? So how do we have the preliminary value of the rebar? So starting point is the alternate load, the alternate moment. But the author know that the ultimate moment gives me a starting point, and he knows that this starting point you need to bump it quite a fair bit, okay, to meet. So if I were to do it, I would bump it to 50%, at least 50%, based on my experience, at least 50%, okay. But he gave it 25% so that he can show you how to remediate. If it is not sufficient, if it doesn't meet it, how do you remedy it? Okay? Alright. Now, here is, so here he calculates rebar stress. From rebar stress, then he compared with the allowable rebar stress and say, okay, whether the crack width can be controlled or not. Okay, whether the amount of reinforcement that we provide can control the crack width below 0.2 millimeter or 0.1 millimeter. Okay? Right. Now, this approach here is conservative. This approach here is conservative. But the consultant likes this approach because it's easier. Okay? So there is a more refined method. The more refined method would look at to calculate the crack width. Okay? That one is much more difficult, so we don't like it. But the contractor like it, or the owner like it, because it will save him money. Okay? The refined method is troublesome for us because we have to calculate more. And then those calculations are not easy calculations. Okay? So as a consultant, we don't like to take that more, I would say more improved step now. Okay? But the guy who is paying for it, of course, love it because he can save the money. Okay? Alright. Now, so the next step is to go and calculate the crack. Alright? Okay. Now this chapter, actually they repeat what they talk about in the early chapter of chapter 4. Okay, here is this one: lateral tension in matured concrete. The design surface crack width may be calculated from equation 610 in section 642, such that, okay, if you, section 642 is in chapter 6. This is chapter 11. So in the chapter 6, they already talk about the calculation of crack width. Normally, it's supposed to be covered in RC1, but most of the time it was not covered now because unless you come out to work as a consultant, if you just in the academic, this is not a practical problem. In the consultant, this is a practical problem. In fact, quite a number of years ago, we have one student. He came back here and we invited him back here just to share his experience. So he worked in the bridge, okay, in the bridge structure. So he mentioned about, he wished that we could cover this side. Okay, so that's the comments of the students. Okay, all right. So here, now if you look at these equations, you know why we don't like to do it, right? Because when you look at it, well, quite complicated, right? Quite complicated. The complication is not only here, the torso here. Okay? So when you look at this thing, you say, okay, how do you make sense out of it? Most of the people, they just memorize. They just memorize the equations. Right? So this equation is W max, the crack width is equal to 3 A crack epsilon m divided by 1 plus 2 bracket A minus C min divided by H minus X. Alright, there are so many symbols there, which you also don't know what it means, right? Okay, and then here it says A crack is the distance from the point at which the crack width is being calculated to a point of zero complete strain. So what is a crack? So we say taken as the surface of the nearest one as illustrated in 11.6. This is a crack. Okay, this is a crack. Let's assume that we want to calculate the crack width here. You can calculate the crack width underneath the rebar or away from the rebar. Alright? So A crack is the distance from the crack where you want to calculate to the nearest rebar. Okay? Nearest rebar. So let's say if you calculate the crack width here, want to calculate crack width here, A crack will be here, right? Okay? If in the middle, then A crack will be like this. Okay? So, which is more critical? Which is more critical? Huh? Huh?
Away from the river.
Away from rebar. How away from rebar? 45 degree.
To me.
In the middle.
Yeah.
In the middle. In the middle doesn't mean it's 45 degree.
No.
Correct, right? Let's say my rebar is here versus here versus here. The angle will be different. It's in the middle, but the angle will be different. So you cannot say it's 45 degree. Right? So it's in the middle. So why is it that the one in the middle? Because the one in the middle has the biggest A crack, right? As compared to one in below, right? Okay? And if you look at the equation, the bigger the air crack, the bigger is your crack. Okay? Right? Okay. C min is the minimum cover to the main reinforcement. Okay? And gamma m is the average complete strain, is based on epsilon 1. Epsilon m is equal to epsilon 1 minus epsilon 2. And epsilon 2, epsilon is a strain. And epsilon 2 is equal to this horrible looking fraction. Right? And this is B bracket H minus X D minus X divided by 3 E SES D minus X. Okay? Okay, so now you understand why we don't like to do this step, right? Right? Because just very messy. Okay? So what is X is the neutral axis distance. H is the growth depth. Okay, D is the effective depth. Okay? Yeah. If you want to understand this equation, okay, this equation, you have to look at this picture. Okay? So this is the neutral axis. This is the neutral axis. This is the X. Okay? This is the H. This is the D. So that explains what is H minus X and D minus X. Right? Okay? So here minus x, h minus x, b is the width, in this case 1000, right? Okay, what is this one? This is a prime minus x.
这个算可是不好像这个是吧？讲它的就是这样子。
Okay, so we have the x, we have the h minus x, we have the b minus x, and then we have the a prime minus x. Okay, so a prime is what? A prime is the distance from the compressive phase to the point at which the crack is calculated. Okay, so let's say I want to calculate here, this is my compression phase, right? So my a prime will be equal to my h. Okay, all right. For the slab, the a prime most likely is going to be the h. For the beam is different because the beam you can calculate the crack width here. Crack width here. You can calculate the crack width here. Okay. No, then if you calculate crack width here, a prime will be this one. If you calculate crack width here, a prime will be this one. Okay. Alright. So the a prime is from the compressor phase to where you want to calculate. So a prime is more for the beam. Okay. If just a slab, then a prime is just equal to the h. Yeah. Okay. So here, epsilon m, that means the mean strain is equal to epsilon 1 minus epsilon 2. Epsilon 2 is this one. Okay. Epsilon 2 is this one. So the value of epsilon 2 is given by empirical expression such that this is equal to this for limiting design crack width of 0.2 millimeter. And this one will be for limiting design crack width of 0.1 millimeter. So if you want to control it 0.2 epsilon 2, you use this one. If you want to control it 0.1 epsilon 2, you use this one. This one and this one, basically they are the same, except that coefficient here is 1, here is 1.5. Okay? This 1.5.
So the equation got in the code.
This one is actually coming from code. Coming from the 8007, which I uploaded, right? So if you look at 8007, you will see this. So the code required for water tank design is this one. ES 8007. Okay? ES 8007. And you find I think it's more in the appendix. Here in the code here, they give you the allowable stress. Okay? For plain bars, 85 and 115, depending on whether it's 0.1 or 0.2. So the book is just taking the values from the code. Okay? Taking the values from
这里可以啊。这样可以的。这样我反正不是要带5本书。对啊。
So at the appendix of the code B2, the assessment of crack width inflection, W is equal to 3A crack epsilon m. Okay, that's where we have the what? Okay, here you can see this epsilon 2 for the 0.2 millimeter crack width. This is epsilon 2 for 0.1 millimeter crack width. Okay, so these are actually coming from the code. Okay, it's coming from a book, but it's actually quoted from the book.
Then sir, the graph for the pre-stress one, the four equation,
啊
那个多多少多那个四个 equation
啊
会在会给啊，在 school 吗
sakit hati.
不需要用到。Okay, alright. Okay, so I. Okay. Alright. Yeah. Now. Okay, let's come back to here. Let's come back to here. W is 3a crack epsilon m. And epsilon m is, say, epsilon 1 minus epsilon 2, right? So now I have shown you how to calculate epsilon 2. But what is epsilon 1? Okay, what is epsilon 1? If you look at this one, we say epsilon m is equal to epsilon 1 minus epsilon 2. This is a string. Okay, epsilon 2 is given by this. Okay, given by this. But what is epsilon 1? Epsilon 1 is a strain at the level considered. Okay? Now, over here, we have calculated the rebar stress, right? We have to calculate the rebar stress. The rebar stress divided by ES will give you the epsilon S. That means the strain in the steel. From the stress in the steel, we have the strain in the steel, right? Okay. So these are neutral axis. Okay, this is our rebar. So this one is the epsilon S, the strain. Okay? And this is the crack level. So this one will be our epsilon 1. Okay? Understand? So the rebar stress divided by ES, we get the strain in the rebar. But we want to find the strain in the concrete, not in the rebar. Okay? So the strain in the concrete which is below the rebar, right? So the strain will be more, right? Because the way that we bend it is like this. The further away, the further is the strain, right? So basically you use a similar triangle, right? Okay? Basically you use your epsilon 1 is equal to epsilon S multiplied by a magnification factor, right? And that magnification factor is what?
over D.
Hmm?
H over D.
This one? What is this one? This will be H minus X, because this is X,
Oh yeah.
right? This is H. So H minus X is this one, this distance here. And this will be D minus X. Okay? H minus X is always greater than D minus X. Right? It could be 1.1, it could be 1.05, and so forth. So you multiply by sigma S, epsilon S will give you epsilon 1. Yeah? So now epsilon 1 minus epsilon 2 will be epsilon m. And epsilon m will be here. Okay? And then you can use to calculate the crack width. Okay, so 1 plus 2 bracket A crack minus C min divided by H minus X. Alright? So in our next lecture, we will use the same example that we have just gone through. Just now we have gone through to the stage of calculating the rebar stress, right? And then the author just stopped. He didn't go ahead and calculate the crack width. So we will use, the next lecture, we will use this formula to calculate the crack width.
So meaning that this one will come up.
Yes, that's why. So but the rebar stress now. So let's say part A, part B, right? Let's say question 2, 40 marks, right?
Can I?
Part A, calculate the rebar stress, right? Part 2, calculate the crack width. Now, if you were the lecturer, right? Which part would you give more marks to? Part A or part B?
A.
Okay.
Reason?
Because A need to give mark to B, if my A wrong, my B also wrong. So I help the student.
Yeah.
Huh?
We need to make the student easy.
Yeah, I mean to make your life easy, I should give more marks to A, isn't it? Because most likely part B you have difficulty. Correct. Most likely because part B is more difficult to do, right? Correct, right? Part A is easier to do. By right, easier to do, I should give less mark, right? Correct, right? But if I do that, maybe you will fail, right? So that's why I will give more marks to part A than part B. But what I'm saying is, you know, next time if you are the developers, right? You are the paymaster. You want the engineer to do part B, correct? Correct. So, so I just stop here. Yes.
如果我的在上面 cliff 嘛，我的 crack 在上面 above neutral axis。
This one.
Yeah, but 我在做这 folding，然后我的 crack 在 neutral axis 上面。So when 我去到这个 crack width 这边，我就不能用那个 cut angle 来算了。
什么意思？
因为你讲那个 cracking 是在compression 的位置，如果那个 crack 是出现在 compression 的位置，
在 tension 的位置吗？
他讲假设是出现在 compression 的位置，
No,
要
no.
两双。
Yeah, if it is compression, the compression will close the crack. You only have crack when you have tension, right?
compression impact，
How can compression you have crack?
因为有
Okay, how does the crack forms? The crack forms is like this. Compression. How can you form the cracks in the compression? You cannot form because
这样子可以。
huh?
如果一条 beam 嘛，然后上面虽然是 compression 嘛，它上面一点 crack，下面一点 crack。
Okay, so what he is saying is like this one. Draw here. Draw here. So if I apply a load, right? Where does the crack occurs? Occurs right here, right? Okay, and then you may have cracks here. This is the shear. Okay, these are shear cracks. So we are now dealing with this one first. You are saying that the crack will happens here. Let's say this is the neutral axis. Are you saying that the cracks is happening here? Huh? Maybe. In fact, this crack will not propagate up to here because at the compression, you are going to have some crushing. You are going to have some crushing here because of the compression crushing. Of course, the compression crush, of course, you cease falling, but that is not crack. Right? I mean, if you test it, right? You see cracks, right? But that is not due to, that is because when you press like this, how does the crack occurs? When you do like this compression, right? How does the crack occurs? Does it crack like this, or crack like this? Which one do you think? You see this one, right? You see more or less like that, right? Because when I compress it, there's actually a lateral tension because of the Poisson ratio. So that one is due to the lateral tension. Because when you press something, this is going to bulge out one. Correct, right? Why a bulge out? Because remember in your mechanics of material, we talk about the Poisson ratio. When we have an axial, we will have a lateral. Okay? And the lateral is actually causing the cracks. When I went to the graduate school, the professor told us that there is no such thing as compression failure. Compression failure is actually a tensile failure. So what do you mean by that? You see, when you press it, these things tend to further apart, and that causes the crack. That causes the integrations. Because the integration is fragmented. That means cracking is actually the loss of chemical bond. Because things are hold at the atomic level, at the molecular level, they are hold on by the molecular forces. Okay? Alright? So when you are blown apart, when something is blown apart, why are they flying all over the place? This actually further apart. Compression is what? That means compression is coming closer. When you press something like this, when it fails, right, you can see all these fragments flying apart. Flying apart, that means it's detached. That means it's actually tension. Why tension? Because of the Poisson. Understand? That means you see, when you compress, because you cannot destroy an atoms. You can only, when we say the failure is actually the molecules and molecules, the bonding actually break up. So how do you break up the molecule bonding? The molecule bonding is attraction, right? So to break up the molecule bonding, you have to use a tensile force to break it.
这样我的 beam 不是 rectangle， 它是那时候那个 assignment， 然后
What do you mean by this when you want to draw out?
momenting 这边 crack， 这样，还是这边 crack？
Because you cracks here, the tension, where is the tension? Unless you have a moment like this, right? But when you have a reverse movement, then this is a tension. This will be a tension zone. Let's say your member is here, like this. When you apply loading, it will be crack here and there will be crack here. Your crack here is because your moment is like this, and this is in tension. So this is actually a tension crack. This section, this is a compression phase. This section, this is the compression phase. The top is not always a compression phase. Okay? So you need to differentiate between top and compression phase. So you always, in a simple beam, simply supported beam, of course the top is always under compression because our moment is like this. But if for a cantilever beam, the top is a compression. That is why if you have a cantilever beam, you break from the top first. Okay? if you press this one, it will break first.
Then my
Because-
rebar should be on top.
Huh?
这样我的 rebar 放上面。
Yeah, of course. In a cantilever beam, that's how you put your rebar. Correct, or not, right?
对对对对对。
Okay. You put the rebar at the tension face. Okay. Alright. Okay. I think now 11:52. So on Wednesday, okay. On Wednesday we will continue, but Wednesday our class is from 12 to 2, right? 12 to 2. Now, I need to move it further. I wonder whether 4 to 6 you guys have class or
4 to 6, no. No.
huh? Wednesday, only Wednesday.
Nói đạt cho
You
rồi.
have class from 4 to 6.
No.
You don't have class from 4 to 6.
Yeah.
What class? Huh? The 2 to 4? 2 to 4 you guys have class or not?
2 to 4, yeah. Yeah, we have class.
Huh? 2 to 4 you have class?
Yes.
How about tomorrow? Tomorrow you have any because tomorrow my class, I only have class from 2 to 4. So can I find a time Tuesday? Thursday I have 6 hours of class, so very difficult to slot. Huh? Tomorrow 10 to 12. You guys have class on?
No.
Huh?
When
Class. Okay. So tomorrow we'll move our class from 12 to 2 on Wednesday to tomorrow 10 to 12. Okay. 10 to 12. The question is the classroom. Our classroom is B5, right? B45, right? B405. Okay, we go to B405 first and see whether we can. Okay. The reason is on Wednesday I have to rush to the Malacca High Court. So I have to actually can come back in the evening because I was engaged as a expert witness in a construction project legal dispute. Okay, so one of my friends who I know for quite a long number of years, so he was a consultant for these projects, and so there was a dispute among the 3 parties. We have the owner, the consultant, and the contractors. So these 3 parties. So each party engage an expert witness because the reason when you have this is because they are failures. They are failures in, there are crackings in the slabs and so on. So when there are cracks, everybody is suing everybody. And it's your fault, it's your fault, it's your fault, you know, etc. So my friend, because he is the owner is suing my friend for 10 million. 10 million Malaysian ringgit. Well, if my friend has 10 million, he doesn't need to work a regular, right? Right. So, and it has to do with the vibration of the floors, because that one is actually a factory. So, and vibration
Makanya
you
sering
have
bilang
office
kalau dia
running
gitu dia nggak akan
on
kerja
floor.
lagi.
Okay. So carrying these things. So the dispute is like this. So I have to kind of.
Mau juga. Ben ya.
So he's suing my friend and his brother. Mainly it's his brother because the company belongs to his brother. So my friend just 1 year my senior, and his brother is 85 years old already. Why you want to sue a guy who is 85? Right now, right? So and the lawyer also 80 something years old. So we just pray that they don't, you know, they live long enough to see the end of the trial. But it's actually, this is the first time I appear in a court as an expert witness. Okay, so and so of course this case is very technical in nature, very technical in nature. So even the lawyers, they know the law, but they don't know the. So when you explain to them what is moment, what is, so they don't know. So you have to explain to them in a layman language. Okay. So the law. So I have to sit down with the lawyer and tell him, explain to them what is the essence of the issue. Okay. So the lawyer asked me, he said, what kind of question should I ask the guy? You see what I'm saying? Because very technical, because this lawyer mainly handle criminal case. Okay, normally in the court of law, we have two kind of cases. One is a criminal case. One is a civil. You know what's the difference between criminal and civil? What's the difference? Criminal case, if you are found guilty, you go to jail. Civil case, you are found guilty, pay money. Right? So this lawyer, I mean, to fight this kind of, the lawyer my friend engaged, he is an expert in criminal law. Criminal, that means robbery lah, or, you know, all this stuff, right? So that's why we need to tell him the technical aspect so that he can ask intelligent questions.
赚多少钱好像？
Huh?
你有收钱吗？
He asked me whether I let me say this. So we have 3 parties, right? 3 parties. So we write the report to defend our client. So the developer, that means the owner of the factory. So he's a rich guy. So he engaged a very expensive lawyer. Very expensive lawyer. I tell you how expensive it is. before the trial starts, right? We go to that office, have a meeting, because the judge is also not a technical person. So he say, okay, there are so many experts, right? So the judge say, okay, why don't you engineers sit down together, okay, and write down what you agree, what are the points that you agree, and what are the points that you disagree, and why you disagree. So you write it up and let me see before I sit before the trial begins. So we went to the owner's lawyers. So owner's lawyers. So we went there. Office is a big office. So on the counter, they have this so-called fee schedule. Fee schedule. That means how much they are going to charge you. So their director level. Let's start from the junior lawyer. Junior lawyer, their fee is 1 hour, 600 ringgit. That means you talk to him for 1 hour, you pay 600. Okay. The top director, 1 hour, 1,008. 1,008. That's the most. The contractor also has lawyer, right? The contractor engage a consultant. So the consultant the contractor has a consultant which has a PhD, Dr. Kriben. so I know him quite well also. So we are on the opposite side. So, so the contractor told my friend, he said we pay 200,000 for the report. 200,000 for the report. Of course, I don't charge 200,000 now. Right? My report is maybe only less than 20%. Okay? But I'm doing my friend a favor. So this is the first time actually the first trial is in middle of August. At that time we just started at Shenzhen. So I went for the first trial because the factory is in Malacca. So that's why the trial is in Malacca. Okay, so I don't know Malacca well, so actually I have to find out where the high court is and so forth. So and it's taking a long time because I suddenly find out that, not to say I realized the judge he don't just handle one case, you know. He just like he handles several cases one. So your case okay, this week maybe from Monday to Thursday, so I hear your case. So of course he will not able to finish it. So his next trial is not like next week, it will be like 2 months later. You know, so now this is the second trial. So second trial is in end of this month. The starting date is actually this Wednesday. This Wednesday. For me, I just want the lawyer to tell me when should I appear? When will I be called? Because I cannot sit there the whole day to listen, correct enough, right? Because I mean I have my class to conduct. So the lawyer said, Mr. Chia, look like they will only call you to appear in the court next year, next January. Okay, next January. So, but I need to actually, you know, just now I told you my friend's brother, 85 years old, he lives in KL. So the other day, last week, he called me. He said, Mr. Chia, can you send me to Malacca? So he said, otherwise I would have to take a bus. So now you know, he walked with the stick, you know, the stick one. So, I think Malacca. So I say, then I told you, okay lah, I in the morning I send you to the court, and then after I drop you there, then I'll come back here. So that's why, so that is why I think that's why in the I think if I leave KL in 9 o'clock, I would maybe reach Malacca before noon. So I drop him and then I come back here. So of course I would miss the 12 o'clock class. That's why, to be safe, actually I want to push it to 4 o'clock. That's the reason.
So tomorrow.
Okay, tomorrow. Tomorrow I think I'll be. Okay, see you tomorrow.